So you need to be looking at standard V2. And I forgot to grab... Alright. This standard builds on the previous one, the one we did yesterday, in several ways. The main difference is that we're no longer finding just area. We're going to be finding volume. We're going to find the volume of rotating objects using a method very similar to the last standard. You're going to need to envision 3D objects given a two-dimensional graph. Now, I'm going to have some pictures to help you with some of these examples we're going to go through today, and I'll show you a website that you can use tomorrow to help you envision it if you're having a hard time envisioning it. We will use integration to find volume by imagining slices of our rotating object in the shape of discs or washers, and then writing out a function that represents the area of the base, the disc or washer, times the height or the thickness of the slice. The figure below shows how this applies to rectangular solids. So, like if we were going to find the volume of an object such as this, you would take the length multiplied by the width and multiply it by the height. But you're given, this is a solid object that you're given in this case, and the ones we're going to look at are created by graphs that you have to envision spinning around an axis. If a solid has some other shape, the volume still equals the area of the cross-section, because notice the cross-section, this is your length times width, length and width, times the height. Because it varies, that's why we need to use calculus instead of formulas. Let me find my first picture here. Okay, so before we turn to the first example here, actually to the steps or techniques to finding it, I want you to know that this is very similar to what we did yesterday. Yesterday we were just finding area. Today we're going to be finding volume. But you're still going to envision taking slices or breaking it up into separate pieces and then adding up all of those volumes. So, like another way I could find the volume of this figure is to take out a chunk of it. So if I was to slice it and take out a piece, much like this was a loaf of bread, taking out a piece of bread, you could figure out the whole volume by slicing up all those little pieces of bread, finding the volume of each one of those pieces, and then adding up all those separate volumes. Now, it seems silly to do it for an object like this because this is a solid object with straight edges, and so length times width times height gives us the volume. But when you have a curved object that's spinning around an axis, so here's my curve, and then as it spins, it creates this solid vase or something like that. Then you can't just multiply length times width times height because it varies the whole way. Yeah, the base is a circular slice, but that circle changes shape, and so it's really tiny down here, and then as you get closer, the circle gets bigger. So because it varies, we can't easily slice it up, find the volume of each separate piece, and add them all up. So we use calculus to do that because calculus lets us do it all in one step instead of breaking it up into pieces. So let's talk about the steps. Steps are techniques to finding volume of solids by plane slicing. So this is like you have a solid, because it varies or it's not straight edges, we're going to use calculus to slice it up into pieces and then add up all those pieces, much like you do with Riemann's sum. You break it up into rectangles, add up all those areas of the rectangles. Now we're just finding volume. You're going to draw a graph of the representative area that we rotated to create your 3D figure. In that area, you're going to draw a representative rectangle perpendicular to the axis of rotation. If rotating around a horizontal axis, the width of the rectangle will be dx. Because if you think, here's my horizontal axis, if I draw my rectangle, and then that rectangle is spinning, the width of that rectangle or that slice is going to be dx because it's an x length. If rotating around a vertical axis, so if now my axis is this way, so we've drawn my rectangle this way, and now it's spinning around there to create a shape, now my width is a y value because it's a y length, so it's going to be dy. And again, remember that the reason it's dx and dy, this is another way to write change in x or change in y because d means derivative, and derivative is rate of change. So because with calculus you are taking an infinite number of slices or chunks or different volumes and adding them all up, we can't give it a specific value like we can with Riemann sum, because with Riemann sum we know how many rectangles we're using. Here we're using an infinite number of rectangles, so we have to use dx. Okay, then for step number 2, much like our last standard, you're going to write an equation for the volume. Now, there's going to be two different shapes that you have. When you have an axis of rotation and you have a rectangle that butts up, so let's say my curve kind of happens like this, the one that's going to be rotating, and you have that represented rectangle butting up to the axis of rotation. Well, as that spins and creates a figure as it spins, what I'm envisioning is taking this rectangle and spinning it around the x-axis. You don't have any gappage. There's nothing left open because it's right up to the axis of rotation, so it creates a disc. The other shape that it might create is a washer. So let's say we have a curve, and maybe our chunk of area is right here, and then you draw a representative rectangle, and then as this spins, you're going to have this gap created, because as it spins, it would be there. So since you have this gap that's created, you're going to have a washer shape. So it's either going to be in the shape of a disc or a washer. If you have a disc, which, sorry, this should be spelled with C, no gaps between the representative area and the axis of rotation, then you're going to use pi r squared as your area of the base, because if you have a disc, then it's just a solid circle. And the radius is determined by the functions, which we'll talk more about that later. If a washer, so if there's a gap between the representative area and your axis of rotation, then you're going to use pi r squared minus pi r squared. Now, where the r values here, you have to think of it as you have a large circle, and then your gap is a small circle. So it's taking the area of your large circle and removing the area of the small circle. So large circle, small circle. As a general rule, when you're using the functions to write your radius, part of the equation, use top minus bottom or right minus left. And as we do examples, I'll explain more what that means. Okay. For number 3, once you get your equation set up, you're going to integrate. Now, when you integrate your equation, that's the easy part because you're going to have a pretty simple function, usually. This represents you finding the volume of an infinite number of discs or washers and adding them all up. Pay attention to your limits of integration. When the equation is in terms of x, use x values. When the equation is in terms of y, use y values. Okay, and this is all dependent on the axis of rotation that you use. Alright, so for example 1, the region under the graph of y equals x to the 1/3 from 0 to 8 is rotated about the x-axis to form a solid. Find the volume of the solid. Alright, we are going to start by actually graphing this function. So, x to the 1/3, and I'm going to change my window so it's from 0 to 8, and I might, and I'm going to change my window so it's to 5, so here's my graph. I'm going to sketch it as best I can, marking that this is 8. And it looks like, I'm going to go maybe up to 2. So just to sketch it. So this is the area that I'm going to be rotating. All right. So if you envision this chunk here spinning around, you're going to have like a solid figure. So it would be, what's the shape that would be like? Like, I don't know, just a piece of, if this was a piece of metal and they were spinning it around to form a solid figure, then you'd have a solid, almost bullet-shaped expression. So maybe to show that as best I can in a two-dimensional world, it would be spinning around like that. Okay? So we're going to draw a representative rectangle in my chunk of area that I'm looking at that butts up to my axis of rotation. So you draw it perpendicular, and it says I'm rotating around the x-axis. Now that rectangle can go anywhere because it's just representative, so I kind of have a picture to work from. Alright, so now I have to write my volume equation. Now, I know I'm going to be integrating from 0 to 8. And you almost have to think of, okay, this rectangle is spinning around to create a solid disk. There's no gappage between the rectangle and your axis of rotation, so it's going to be a disk, which means I'm going to use pi r squared because that makes the area of my base a circle. Now, the radius, so I'm just going to throw pi r squared here. Well, let's go with this. The width, because remember this is like a slice, you can't have a slice of no depth. So maybe draw in a depth. Okay, so there's my depth. My depth is going to be of this width as that spins around. And the width, since it's an x length and it changes, this would be representative of my volume equation. So this is the volume of the base, because the base slice, if you were to pull this out and look at it, like that, the base is a circle, and then we have to multiply by the height to get the volume. So this is my volume equation. The reason I have to set it up as a volume equation for that slice that I'm taking out is because I'm looking for the volume of the whole figure. And by integrating from 0 to 8, it's like slicing it up into all these little disks and adding up all the volumes of those little disks. Alright, now I can't integrate this yet because not everything's in terms of the same variable, so I have to replace that r with something. And that rectangle that you draw in helps you because that rectangle is going to represent the radius. So, since we're working with a vertical rectangle here, to write the radius, you're going to take top minus bottom. Like if I knew what that value was, like let's say that value is 1.8, then I know the length of that would be 1.8, or my radius would be 1.8. But I know over here, it's going to be like 1.2, maybe. So I can't write in 1.8 as my radius. I have to write it in as the function, because the function is what varies and changes the radius as you go along this figure. So top minus bottom, that's how we're going to write the radius here. Top value is the function. So we're going to put in x to the 1/3. Now I'm going to move that pi out front just so you know. That's a constant. So we have x to the 1/3. Now to get the length, you usually have to take the higher value and subtract the lower value. But in this case, my lower value is 0. So we don't have to put in my 0. So top minus bottom just gets me x to the 1/3. Now, I will tell you, this is the biggest mistake that happens, is that people plug in for the radius and do that correctly, but then forget to put the square back on, and then it messes up their answer. So make sure you have the square there. Simplifying, power and power, multiply them together. Okay, so now I'm going to integrate and evaluate it from 0 to 8. When I integrate, I'm going to add 1 to the exponent to get 5/3. Dividing would get me 3 pi over 5. times x to the 5/3, and I'm going to evaluate that from 0 to 8, which really, I know plugging in 0 is just going to get me 0, so I'm going to plug in 8. So 3 pi divided by 5 times 8 to the 5/3 gets me 60.319, and this is going to be units cubed because you're talking about volume. Okay, so to kind of show you what that figure looks like, I can kind of show you this example here. So like this is the same area, and then this is the 3D figure that would be created. So you can kind of see that picture better of the slice taken out, and then if it's rotating around, the kind of figure that it would create. Alright, let's look at the next one. Example 2. Alright. The region in quadrant 1 bounded by the parabola y equals 4 minus x squared is rotated about the y-axis to form a solid. Find the volume of the solid if the dimensions are in inches. Okay, so we're going to first graph that. 4 minus x. Oops. 4 minus x squared. Okay. Change my window a little bit. I don't know what my bounds are yet. Oh, and it's just the region quadrant 1. So I'm going to start at 0. I'm going to go to 10 for now, and then my y min, I'm going to make -1, and y max would be, oh, no, I'm going to go from -10 to 10. Just, okay. And actually, I'm going to change this to -10, because I just realized that you're rotating around the y-axis. So, okay. So this is my figure. I'm going to zoom in just a little bit more by making my x max from -5 to 5. And my y max to 5. Okay. So it's this section here. So I'm going to graph that section. Because it just says the region in quadrant 1. So this is the region in quadrant 1. It's bounded by that, and it's rotated about the x-axis to form a solid. Now, when I draw my representative rectangle, sorry, the y-axis, I have to draw it perpendicular to the axis of rotation. Okay, so that changes my problem a little bit because now I have a horizontal, which makes the width or the depth of my slice a change in y. So it's going to be dy for the depth. And so this would be rotated around to form this disc. This is going to be rotated around. So now it's almost like you get the same bullet kind of figure like we had for example 1, but now it's just vertical instead of horizontal. Alright, so let's go ahead and start writing my equation. Now my limits of integration, they were given to me before in example 1, but here I have to find them, which we find them from my y values this time since I'm rotating around the y-axis. So we have from 0, and then the highest point here looks like 1, 2, 3, 4. Now, if you're not sure, we could actually plug in 0 and see that, okay, it does connect at 4. So that would be the height of my figure there from 0 to 4. Now, as it rotates, because there's no gappage between the rectangle and your axis of rotation, you're going to use pi r squared. And again, we've talked about that since the width or the depth of my slice, because if I took this out, it would look like this still. That's a y value this time because it's a y length, so we have to have dy. Alright, so now we have to write my radius. Now, with the radius here, because my my rectangle is horizontal, I have to go right to left, because going top to bottom doesn't make sense. So, right to left, or right minus left, gets me that length, or that radius, of the disc, because like this would be right here. Okay, so that gives me the radius. So right minus left, the right side of any one of those rectangles, no matter where I drew it in, would be trapped by that function. So the function is going to be on my right side. Now, because everything has to be in terms of y, I have to write my function in terms of y. So we have that. And then I'm going to divide by a negative. Let me just make sure. Yep. Okay, yeah, I'm going to divide by a negative. So I get 4 minus y equals x squared, and then square root everything. So x would equal square root of 4 minus y. It's the same function that's bounding it, but now it's written in terms of y. So I'm going to, for the radius, put in the length of this, which would be right minus left. Well, the left is 0, so it'll just be the function minus 0. Since my function is square root of 4 minus y, remember to square it. Do that. Okay, again, you have to rewrite your function, since that's your right bound here, in terms of y, because your depth of your slice is in y. Now, this square is going to cancel out that square root, which is nice. I'm going to bring that pi out front. So integrating actually is fairly simple. We have pi, and then 4y minus 1/2 y squared. We're going to evaluate that from 0 to 4. Now when I plug in 0, it cancels everything out. So now I'm only really concerned about what I get when I plug in 4. So we have pi times 4 times 4 minus 0.5 times 16. So we get 25.133 units cubed. Okay. Let me just check the time here. All right. So we're at 22 minutes. What will probably happen is that tomorrow, which is what, Wednesday, we'll probably go through example 3 and example 4 together in class before I have you do some practice on it. And then your homework for Wednesday night will be example 5, the 4-type problem. Okay, so that's it for this section for right now.